work, energy, power.
Work, energy, power. Words which we'll meet many times in this program. Three very important and closely connected concepts. Well, let's start with energy. What is energy? Well, it's difficult to give a simple, neat definition, but we can say some things about energy. For example, all matter and all things have energy, but some have more of it than others. In fact, everything that happens in the universe ultimately occurs because energy is transferred from the more energetic to the less energetic. And engineers use this process of energy transfer to do useful jobs, like lifting loads, turning wheels, producing heat, light, sound. Well, let's start by looking at how energy transfer is used in lifting a load. Well, here's a load. Now, an average apple weighs about 1 Newton. So we're going to imagine that this rather surreal apple weighs exactly 1 Newton. And if I lift it up, I'm transferring energy to the apple. Moreover, I'm exerting an upward pull of 1 Newton to counteract the force of gravity. Now, in order to lift it over 1 meter, say, requires a certain amount of effort. And it requires the same amount of effort to lift it a further meter. On the other hand, in order to lift 2 apples, 2 newtons, I have to exert twice as much pull and therefore twice as much effort in order to raise it through the same distance of 1 meter. Well, here we have a means of actually quantifying the amount of energy transferred in terms of the load lifting effort. If I lift so many newtons by so many meters, that requires a certain amount of effort. And engineers call this load moving effort work.
They define this as force times distance. We can now talk about the work done by a force on a body. When a 1 Newton force moves by 1 meter, 1 joule of work has been done. And applied over a second meter, the total work done on the body by the 1 Newton force now becomes 2 joules. In general, a force of F newtons acting over S meters will have done Fs joules of work on the body.
So when we say a force has done work on an object, we're also saying that energy has been transferred from the thing producing the force to the object which moved. Now, I did work in raising these apples, and the work done, or the energy transferred, is given by the force times the distance. 2 newtons over 1 meter, 2 joules. In this case, 1 Newton over 2 meters, again, 2 joules of work. So there we have the relationship between energy and work. We can think of energy as the capacity for doing work, or work as the amount of energy transferred. Now, we're not just concerned with the amount of energy transferred. As engineers, we're also interested in how quickly that transfer can take place.
Yes, that's right, and the term we use is power, yet another word with a precise meaning in mechanics. Have a look at this. Two identical amounts of work have been done. 100 newtons in each case moved through 1 meter. That's 100 joules of work. But obviously they were done at different rates. And that's because this one has a more substantial, a more powerful motor than this one. This one can do that work in 2 seconds as opposed to 8 seconds here. So that's 100 joules in 2 seconds. That's 50 joules per second. We call that 50 watts. Here, the rate of transferring energy was 12.5 watts. So that's how we define power, as the rate of doing work or the rate of transferring energy. We measure that rate in joules per second or watts.
For a person at rest, the human heart has a power of 7 watts. The heart's work rate is about 7 joules per second. A horse is capable of a power output of about 500 watts. In fact, the unit of power called a horsepower is 746 watts, based on experiments carried out by James Watt in 1784 using a strong dray horse. And a modern train is capable of a work rate of about 10 megawatts, that's 10 million watts. Well, these are just 3 examples of different work rates you can expect from work-performing systems.
So the concepts of work, energy and power are closely interrelated. Well, for the rest of the program, we're going to look at mechanical energy in various forms. Now, you'll remember that I transferred 2 joules of energy to this apple, from which you might infer that this apple now has an extra 2 joules of energy here that it didn't have when it was on the ground. And you'd be right. But in what form is that energy? After all, the apple up here looks exactly the same as it did when it was on the ground. However, if I were to release its support, then gravity would do work on the apple to bring it down to the ground and beyond. And we call the energy that the apple has up here compared to what it had on the ground, its gravitational potential energy. Now, if it has energy, it should also be capable of doing work. Well, we can show that by connecting it up to another apple. We'll use this pulley, and if I release it, you can see that the 2 joules of energy have been transferred from the first apple to the second one. And I can continue this process if I transfer this to another pulley. I can use it to lift these 2 apples. And again, 2 joules of energy have been transferred. So in each case, the 2 joules have been transferred from mass to mass to mass. But remember, those 2 joules came from the original work which I did in lifting that first 1 Newton apple 2 meters. Well, raising weights above the ground is one form of storing energy. But we can also store energy in a spring. And I can show that by transferring these 2 apples over to this spring. And if I release the spring, those 2 joules are now distributed amongst the gravitational potential energy of the apples, the energy in the spring, and the energy in the motion of the apples. Well, let's look at those other forms of energy.
Well, the energy of motion is called kinetic energy, and the energy stored in a spring is spring potential energy. It's quite easy to think of a spring storing energy. When I pull back on the spring, I'm doing work on it. That transfers energy to the spring. That's spring potential energy. When I release the spring, it in turn does work on the ball, leaving the ball moving at the end of the motion. That's energy of motion, kinetic energy. Well, here we have 2 forms of energy, kinetic energy and spring potential energy. We'll concentrate here on kinetic energy. So we'll look at the ball alone, and here we'll assume that the ball of mass m is acted on by force r over a distance s to reach a velocity v. Well, the work done on the ball is a product of force by distance. That's W equals RS. And the force can be expressed from Newton's second law as mass by acceleration. Now, the acceleration is the change in velocity, that's v, over time, t. The distance travelled is the average velocity, that's a half v times t. Cancelling t, we get an expression, a half mv squared. Well, that's the energy transferred to the ball. So we now have a mathematical expression for kinetic energy. So the energy possessed by a body due to its motion is dependent on its mass and the square of its velocity. These two bodies of the same mass of 1 kilogram have different kinetic energies. Applying the formula for kinetic energy, the top one has kinetic energy of 2 joules and the lower one 8 joules. So although the lower body has twice the velocity, it has 4 times the kinetic energy.
Well, this flywheel has kinetic energy too, rotational kinetic energy. Up to now, Terry's been talking about particles moving in straight lines with translational kinetic energy. But if we consider a point mass moving in a circle, then that too can have kinetic energy.
A flywheel is a large number of particles moving in circles. So how do we express the kinetic energy of a rotating flywheel? Well, we can quote an expression just by analogy with translational motion. Remember, from earlier units, we've talked about rotational inertia, or moment of inertia, I, and translational inertia, or mass, m. Also, the rotational equivalent to translational velocity, v, is angular velocity, omega. So, the rotational analogy to the translational kinetic energy formula of a half mv squared is a half I omega squared.
Well, there's a detailed proof of that relationship in the text. Now, coming back to our studio flywheel, to turn the wheel requires energy, and I'm going to use the gravitational potential energy of this 4 kilogram mass as I raise it over 1 meter. Again, the increase in potential energy is given by the work done in raising it over that distance. Right. I'll hold it there. Now, the potential energy of that mass will be transferred to the flywheel and the falling mass as kinetic energy. And once all the potential energy has been used up, I'll be able to measure the speed of the flywheel and of the mass with these meters, radians per second and meters per second. Right, I'm going to start the experiment off, and Terry over there is going to take care of the results. So you can see the potential energy is being converted to kinetic energy. And the final speed of the flywheel is 13 radians per second. And the final speed of the mass as it hit the floor, 0.25 meters per second. Right, over to you, Terry.
Well, I've recorded that information from Tony here. The moment of inertia of the flywheel, 0.463 kilogram meter squared. The final angular speed was 13 radians per second. Mass is 4 kilogram, and its final speed was 0.25 meters per second. The initial energy is the potential energy, which was the work Tony did in raising the mass. That's force by distance, force, mass by gravity. If we use the figures from above, that's 39.2 joule. So that's our input energy. The final energy is made up of kinetic energy of the flywheel, half I omega squared, kinetic energy of the mass, a half mv squared. If we use the figures from above, they come out like this. 39.1 joule of energy in the flywheel, and only 0.1 joule of energy, kinetic energy of the mass. So that's our initial 39.2 joule of energy.
Well, in the meantime, the flywheel has slowed down. It's lost some of its kinetic energy. But where has that energy gone to? Well, it's been lost by friction in the bearings. We'll have more to say about that later.
Well, you may have come across these flywheel-driven toy cars. I do work to get the flywheel rotating. That then stores energy as rotational kinetic energy of the flywheel. That is then transferred as kinetic energy of a car. Well, that idea isn't only applied to toy cars. It's a new idea which is finding its way back into modern technology. And for the remainder of this program, we'll look at energy storage in flywheels.
As far back as the 1950s, this bus in Switzerland was operated using a flywheel. And more recently, investigations are being carried out on the use of flywheel energy storage in cars. The same team of investigators also installed a flywheel energy system into trains on the New York subway. They ran in New York after installation and very extensive trials in California. They're also experimenting with a purpose-built advanced concept train, as it's called. This too has a flywheel energy storage system, and it is used to store the energy of braking, which for normal trains would be wasted as heat. The system works like this. The flywheel has a certain amount of rotational kinetic energy. At the same time, the moving train has translational kinetic energy, which during braking is transferred to the flywheel by electrical means. The flywheel now has increased kinetic energy. This extra energy can then be made available, again by electrical means, as translational kinetic energy of the train, as the energy transfer gets the train moving again.
Well, there you are. We've seen flywheels in cars, in buses, and in trains. The Swiss gyro bus was developed about 20 years ago, but has since been discontinued. But now, new technology has generated a new interest in energy storage in flywheels, as we've just seen. And that interest isn't only confined to transport.
Well, the technology of the flywheel has been taken into space. This sophisticated and compact piece of hardware uses exactly the same principle for storing rotational kinetic energy. In fact, we can use that energy to power a communication satellite. And that's been made possible by advances in flywheel design. Now, there are basically two requirements for any successful flywheel energy storage system. First, we must eliminate energy losses. And secondly, we must make sure that we can store as much energy in the flywheel as possible. Now, in our studio model, friction, mainly in the bearings, caused the flywheel to slow down, causing a loss of kinetic energy. Well, the best way to reduce that friction is to keep the bearing surfaces which cause the friction apart. And we can do that with permanent magnets. Two magnets are attracted to one another. Now, if we can keep these magnets apart, then the forces of attraction will ensure that the two magnets will always stay in line with one another. Moreover, we can use that magnet system in an actual flywheel. In this flywheel system, we have two pairs of magnets, one at the bottom and one at the top. The bottom pair of magnets pulls the flywheel downwards, whilst the top pair of magnets pulls the flywheel upwards. So effectively, the flywheel is suspended in space. Moreover, any deviation from the vertical axis will be strongly resisted. The magnets forcing the flywheel back into its equilibrium position. In addition, an electronic device detects vertical movement of the flywheel and corrects it so that the flywheel stays in vertical equilibrium. The result, a frictionless magnetic bearing with no surface contact. Well, Our satellite flywheel uses exactly the same magnetic suspension system and can operate at high speeds with minimum bearing friction losses. Let's speed up the flywheel. Of course, there is another source of friction, air drag, and this air resistance increases with higher speeds. The energy losses are larger at the higher speeds. In fact, if I switch off the drive motor at about 1,000 RPM, you can actually hear the air windage, as it's called. Well, enclosing the flywheel in a vacuum, which is not too difficult in outer space, effectively reduces those air windage losses to zero. Well, here, a more conventional flywheel is being assembled to store energy back here on Earth. Basically, it's a massive steel cylinder, about 1/10 of a meter thick and 1/2 a meter long. And it can be mounted on magnetic bearings using the same principle as the satellite flywheel. Here's one of the magnetic rings used in those bearings. Well, what's this particular flywheel used for? Well, here's one of the projected applications for use in the French telephone system to provide backup emergency electrical supply. Now, the whole flywheel assembly is housed in this casing, which can be evacuated to reduce windage losses. Well, how much energy can be stored in this flywheel? We can do a quick calculation. The moment of inertia of the flywheel, I, is 9 kilograms meter squared. And it runs at an operating speed, omega, of 12,000 revolutions per minute. So the energy which is stored at this operating speed is given simply by 1/2 I omega squared, which is 1/2 times 9 times 12,000, and I'll convert that to radians per second, times 2 pi over 60, all squared, and I've worked that out already, and it comes to 7.1 megajoules. Well, that's equivalent to the kinetic energy of an average family car traveling at 250 miles an hour. So you can imagine that if this flywheel, running at its operating speed, were to disintegrate, it could cause quite a lot of damage. And that's why these things are buried underground, just in case. Well, here's the flywheel assembled without its casing, but mounted in its magnetic bearings. And I can turn all 350 kilograms of it with just a slight push. And it'll store that energy, even at high speeds, with very little energy loss. Work in, energy stored, power out.